Tonight I'm going to continue doing some testing on this Audi. It is here because of some regular maintenance, and in doing so we noticed that there was trouble code for bank 1 timing related description. I'll have to get a shot of that to you here in a little bit, but he wanted me to look into it and see what the cause of that is, and if it's going to need actual further timing work. He wants to know. It is a intricate, very difficult job to do any type of timing work on this. The whole engine has to be removed. The chain is located in the back. It is a not sure if I mentioned, but 14 RS5. It's a 4.2 V8, and it's crammed in there, and it's not your everyday car as well. So I had done some testing beforehand, but I've kind of been pondering, coming up with some more testing ideas that I want to perform on it, just to get some sort of good detail, insight on what's going on. So other than that, and it's going to involve with basically I want to do some in-cylinder pressure testing, comparing bank to bank. The code is related towards bank 1, and so we supposedly have a known good bank 2 here, so with it. So I want to take some captures, compare side to side. Okay, before getting started, I wanted to just get you a shot of the trouble code that I was interested in, which is that P052A cold start A camshaft position timing over advanced. Yes, there are some other codes in there, but that is the code that actually has returned from a previous visit when it was cleared. So there is something going on enough to the point where it keeps logging that code again. As far as OEM information, not much to go by. Just the description or information on it. It's the cold start monitoring VVT actuator intake target error. So it's not happy with where the intake cam is, and as far as any type of information, as far as anything goes, it just says check the camshaft adjustment valve N205, and that's basically just that oil control solenoid valve. When you go past into that, it just has you checking the ohms, and I don't know if it tells you swap it or blah blah blah, but I can tell you before going further that I did swap the valves, solenoid valves, and it made no difference. And now it's why I want to do multiple tests to see why we keep logging this code again. Okay, so now I've got everything set up that I want to look at. In cylinder on number 1, the transducer. Then I've got all the other ones down there, all the variable solenoids unplugged, and obviously I'm going to be doing a lot of cranking since I'm testing both banks. I want to try to keep the voltage amperage consistent and high. So scope is running. I'll turn on. Okay, so here goes nothing. Go ahead and crank it. And I'm not pressing the gas pedal. Okay. Alright. Go ahead and crank. I've put the plug back in there, switched over to this side, go ahead and crank it. Okay, so wanted to get you a shot of the waveforms for both banks, so bank 1, bank 2, of the cranking in cylinders for number 1 and number 5. Right away, here at about the same zoom level, we are looking at cylinder 1, bank 1, and this is cylinder 5, bank 2. You can tell right away towards the bottom that there is a difference from bank to bank. You're seeing this area, this rise in pressure in between the TDC points that is higher than the rise in pressure in bank 2. And right away, just during cranking, its breathing bank to bank is already different due to what looks like can be a timing issue bank to bank, which would correlate with the code as far as the bank. It's same bank 1, but there's a lot more to try to look at to try to identify what the main cause of the I guess trouble code is. Okay, so now we're zoomed in with the ruler set up, and we obviously get a better visual example of the difference in that rise in pressure. So that typically and normally is going to be when, because you are from the 180 to 360 is the exhaust stroke. Most of the time, typically this will be when the exhaust valve closes as the piston's still in its upright travel towards TDC. So if the exhaust valve closes without intake being open, pressure is going to start to rise until either the intake valve opens or the piston changes direction. So that's why we're seeing that rise in pressure there during the exhaust stroke. It looks to be like that's when the exhaust valve closed. Now compared to this good bank, same exhaust stroke, the rise in pressure, there is a rise in pressure, but it's not as high compared to the bad bank, which most of that time will indicate that the valve still closed during the exhaust stroke, and no intake valve opened up to that point yet. So the piston going up will raise the pressure, but if it's typically higher bank to bank, that means one probably closed earlier, had more time to build and raise the pressure until either an intake valve opened or the piston started to descend down. That is most likely what's going on here, being that the code supposedly is displaying or reading that it is too advanced. So one quick thing that we can do, we can take a measurement of this point when the exhaust valve opens and when it closes and compare them bank to bank. Okay, so bank 1 exhaust valve opening point that we can measure is showing us 83. Now we'll check bank 2, and bank 2 is showing us about 76. So bank 1 is happening about 5 degrees earlier, and then now we can go ahead and check when it closed. Okay, as far as the closing timing, it's looked like about 25, 26 area. And bank 2, it's looking like right at about 20. So about, again, 5-6 degrees of a difference between the banks. Again, this bank 1 happened earlier this way, closing about 5-6 degrees or so sooner than bank 2. That's where the higher blip, higher pressure, more time as the piston travels. That's why you're reaching a higher pressure point, because it closed earlier. And just for comparison, sort of looking at duration from open to close. So 236 on bank 2, and duration on bank 1, even though it's looking like it's advanced, it's about 237. So both are about the same. So I would say that that is the true pretty close to true events of when it's opening and closing, and bank 1 is more advanced on the exhaust side. Now, on as far as the intake, I'm starting by trying to show where I think potentially the duration is. Supposedly opening somewhere in this region and closing somewhere in that region, giving me about 250 ballpark on this bank 2, and compared the same with bank 1, with supposedly opening somewhere in that point and closing somewhere in that area, about just about the same, just one or 2 degrees off. But that at that point, I think it's dependent upon where you put your cursors or rulers, whatever you want to call them. The intake valve closing, bank to bank, we can compare. This one's showing up at about 64, and this one at about 67. So bank 2 looks like it is again more towards the right. So bank 1 is happening earlier. About on this 3 degrees difference is what we're getting measurement wise. So duration wise on intake seems to be about the same, but potentially, possibly, like I said, bank 1 seems to be closing a few degrees sooner. Okay, now cold idle, cylinder 5, solenoids unplugged. And I'll set you down here again, let you enjoy the music. Okay, so now to bring up the captures from the idle, this cold startup idle with no oil control valves plugged in. Basically, now we are going to start up and let it run idle with no intervention from the variable cam timing system on both banks for both intake and exhaust, and see what it looks like running just on straight up timing chain installation position at this point, just like we did when cranking. Right off the bat, this is, we'll be able to visually tell again, this is bank 1, and again, look at the portion down low, that it's much different at idle. This picture here is when idle's been stabilized, and it's the same stabilized point here as well for bank 2. Just for some figures, running compression is about 50. No, that's the difference between two. So it's about 54, and then the high point peak of that pressurized in the exhaust stroke, about 3.7 psi. So it's running at about 54 and about 3.7 exhaust pressurized. So this one's running about 56, 57, and the rising point of pressure about 7 psi. So big difference for sure here at the bottom point. Not so much of a crazy difference up top, maybe what, 2 psi. So the difference on the exhaust about 3.5 psi. Definitely bank to bank should not be that much different, and we know that it's being introduced due to timing being advanced. Alright, so for now, this next procedure that I want to do is measure bank to bank in cylinder, running with all 4 oil control valves plugged in. Now we are running here and should be ready to crank it. Oh, also, I went in, I cleared a bunch of, or all the faults that I had set up to this point, because I wanted to try to activate or run the variable timing as it would normally try to. So I wanted the computer fault free. Now the idles come down. Nice rev. Let it stabilize a little bit, and then we'll shut it off. Okay, so now I'm gonna show you what the captures for the startup and idle with variable cam timing control solenoids plugged in looks like bank to bank. And we are going to start by looking at the good bank 2 cylinder 5. This is your initial startup. It comes down, stabilize, quick rev, and then stabilize again. Obviously we are going to have cam phasing come into play now. Okay, so I am zoomed in towards the beginning portion of the capture and in the lower portion of between the TDC points in the exhaust area, and there is that rise in pressure. I want you to just pay attention as I scroll through the idle portion of this, what this looks like. Now obviously we are zoomed in, but this is also high airflow at the first initial startup, so we do have a high pressure area built in, which it's gonna increase with the engine actually running. That rise in pressure is gonna rise, but again, this is the known good bank. But we're not really right now wanting to look at numbers. I want you to look and see what that looks like as we travel through the idle portion. And so we're scrolling all through the capture, and just keep in mind this point and right there. From that cycle to this cycle, that point drops out. Right there, we're having and seeing phasing occurring. I can't tell you right now whether it's happening on the intake side, exhaust side, whichever side. We know we see phasing occurring, which we wouldn't be able to have if the solenoids weren't plugged in, like the last capture. And so as we continue to go, okay, so now we are at this point where we're going to be in the beginning portion of where it's stabilizing, and we'll continue to scroll. And there you can start to see more phasing occurring. And this is now in its stabilized area, and that's pretty much where it stays at in an idle state with phasing intact and doing its thing. Now this is going to be bank 1, the side that we seem to be having issues with. So we are in the very beginning initial point. Obviously looks about the same, which we know we have a higher pressure range in that area on this bank. We'll scroll through, and there we see phasing occurring. We see it drop down, but it actually doesn't drop down that much compared to the other bank. Actually, it does continue to drop. So more of phasing action occurring. And we're still very early on in the capture, right about that point. And we're starting to already see how it's then coming back. As you can see. And now we are at this point where it's pretty much where it's going to idle, with it phasing however it's going to stay phased in a little bit of a warmed up state. So the measurement that we are going to look at is this portion here. We are at 27 on the good bank when it's stabilized with phasing. In that same stabilized area for cylinder 1, bank 1, that same point in time, it's showing us 37. So about 10-degree difference bank to bank with phasing at warmed up stable point. Again, bank to bank, this same engine should not have this much of a difference, especially during same condition at all points, whether cranking and or idling and so on. Okay, the next step I want to do, again bank to bank, both intake control valves are unplugged right now. I'm going to start up, let it idle, and I am going to manually power up the the solenoid for the intake on bank 1, and I'll do the same for bank 2. Got the meter hooked up just to actually just check and make sure that the pins were actually in the probes. So at the same time, I guess you can check your continuity, make sure I am making contact, and also check the ohms of that solenoid. We'll do the same with that side. But for now, and I'm going to use the jump box to manually give it power at idle. Not sure if you can hear that idle change, but it did make a noise change, so something is working and happening. These high points are when I tap the solenoid. So I'll go ahead and save this, do the same for bank 2, and then analyze them both. Okay, there's the connection for solenoid on bank 2. Same thing. Okay, so here are the captures for both banks, cylinder 1, cylinder 5, with the activation of the oil control valves. And as you can see, where these points are the rise in pressure when the solenoid was activated. So I will show you measurements here when it's stable with no control, and then what the amount of advance is when it is activated. One of the main reasons why I wanted to also do this was to compare both intake cam phasor advancement in amount of degrees to see if it was the same or close enough to the same bank to bank, to also try to help narrow down exactly what is going on as far as pertaining to why the code would keep coming back. So in this captures, we will be looking at the phasing on the intake cams. And the way that I am going to do it is by using the crank signal and the cam signal, and comparing points in those areas to see how much of an advancement occurs. So here's a capture of 720 on the CKP. Here is a gap portion. Here is the other gap portion, and here it is again. So 0, 360, and then from 360 to 720. Up top is the intake cam sensor, and first we are going to be looking at cylinder 5 at a stable point in idle with no solenoid activation, and the point of reference that I'll be using off of the cam signal is this last small tooth before the 720 mark, and this edge where it goes down in voltage, and in between that we'll take a degree measurement, which I've got the cursors there already, and I'll take the same measurement on both banks to get a good comparison. So for this one, at stable idle, we're at 44 with no activation. So we'll back out and then we'll go to a point of where we first did some activation. And what I'll do is I'll take about 3 measurements to get a good average or comparison. So I'll do during this cycle, this one, and this one. And this is the beginning of the activation. So we'll do about these first 3. Okay, so the first measurement here is, you can tell the distance from the 720 over to that edge has increased, or has moved more to the left because we've advanced it. And we're at about 83 degrees for that first point, so we'll write that down. And then we'll move on over to the next cycle. Okay, and then the second cycle there, we are 82. And on this third cycle, we are actually getting 90. So as far as what we got is, our starting point was 44 degrees. These are our travel points that it reaches, so the difference, the amount of advance that we have going on cylinder 5 bank 2 intake is going to be 46, 38, 39. That's part of the reason why I did multiple points, despite being that you're giving it a steady amount of 12 volts. Just what I've noticed on off camera, it's just not a perfect world of, despite, even though you're giving it 12 volts and holding it, that it's going to reach a certain amount of degrees and be that and hold that exactly all the time, cycle per cycle. No, it kind of just bounces around. That's just what I've noticed from taking multiple measurements with both banks. Now over to cylinder number 1. This will be the stable idle measurement with no oil control valve, and 45. So basically about the same starting point. And so we'll now take about 3 measurements here on the first 3 cycles of solenoid activation. Okay, so there's our first measurement from here to here, and here we are actually getting about 75. And the second cycle measurement, we are reaching about 80, we'll call that 85. And then our last measurement would be 81. The way that cylinder 1 looks like, again, we start at 45. These are our travel points and the amount in degrees, so 36, 40, 30. Not 100% exactly the same, but still traveling about the same. This one was a little bit high of a travel. This one was a little bit of a low of a travel, but again, they do reach roughly, estimately about the same travel. It's not always 100%. I can guarantee you, I've gone over these multiple times in different areas, and it's never 100% the same. Which was another thing to learn that I learned on this when taking all these measurements in different points. You would think that you would have a definite reach point, but it's pretty crazy and cool, whatever, to see the target bouncing between certain amount of degrees, cycle to cycle with full voltage, which is just gives you a mindset of how crazy that it is that the computer with duty cycle has to try to hit targets, um, you know, multiple times, multiple areas of the RPMs and everything. It's pretty amazing. But again, doing and checking this advancement testing to check and see the phasers on the intake, being that the code again was related to an intake cam area, the intake cam performance or timing, and so I wanted to just see. I'm trying to just narrow down as to what is going to be needed, being that this is such a big job to do. Alright, as you can tell by the obvious, we've got the engine removed from the vehicle, and I've got the upper timing covers removed, got valve covers removed, and I'm going about just setting it at the timing checking point or setting point. And before I take anything apart, I just wanted to see where the cams and everything are lined up, just to get a better idea of physically seeing compared to the scope capture. So the way you go about it is rotate the crankshaft pulley, and with this locking pin tool, you insert it through there and screw it into the block. So that is the setting point, and then the cams will point up with these two screw holes on both sides, and they'll be pointing up. Obviously, this is for being able to set the timing tools up here, which is these guys here. And just before turning the camera on, I noticed something that was slightly different bank to bank. So this you just simply set on here on the flat portion, and you screw down the bolt in there, and that'll lock your cams in position along with your crank being locked in. This is bank 2, the bank without the trouble codes, and if you notice, this is how I noticed the screws lined up and were able to be screwed down without any effort, pretty much. And when I was setting this side up, I noticed that see, this one's already stopping. This one's not even lined up. So this is bank 1, the one with the trouble codes. The cams aren't perfectly lined up as far as in the true correct position of being flat up and down when being in the locked position. So we definitely do have a physical timing, positioning, or alignment issue going on here. Not necessarily looks like not necessarily a performance type due to phasers, unless there's an issue with this phaser, but not 100% sure yet. But it seems like the exhaust cam, more than the intake possibly, it's shifted this way. It's obviously hard to tell on camera, but I believe that both of them might be off, but it definitely looks like the exhaust is more shifted inwards. Again, very difficult to tell on camera, as opposed to these two are pretty much perfectly flat. Obviously, well, they are, because the timing tool goes in without any extra effort. So that was the first thing I noticed, and I just wanted to go about getting a better idea. So I started to do some measurements, and that way I can maybe show you on camera, hopefully. So what I'm doing and using is this tool that I have with the dial indicator, and the top on these Audis, the top of this cam cover basically is a machined flattened surface, kind of like the top of a cylinder block. So I can use that to be able to do a true depth measurement and check for differences. So I've gone ahead, and at this point I've got it zeroed out, and I can go ahead and I'm going to use this inside edge here and here to give you a reading and to go across. So basically what I'm doing is I'm going to compare this known good side, see how much it drops from the surface down to this flat surface, and also run it along to check the flatness, or how perpendicular or parallel this is to the surface, and the same here. So so there, it's on, I'll call it the deck surface, and if you see, it's at about the 45. That big needle is on the 45, and if I roll it down that way, we traveled to about the 51, and actually right at the 52, right at the bottom portion. So it went for 7,000, and now I'll do the same here on the exhaust. Oh, let me get, okay, so there, and we are, looks like about 47, and travel, and it's still at about the 47, which, so what that means, this exhaust cam is 100% perfectly straight and flat as far as this portion compared to this deck, since the point here to here compared to here stayed the same. That tells me that's truly straight up and down and flat. This intake one moved, the difference from there was 7,000, which obviously is minute compared to, well, it's minute enough to where the timing tool still lays on it flat enough, and there can be, and I know on BMWs and stuff, there is a tiny bit of play, or can be a tiny bit of play on with the cam gear, but there is no hex on the cam to be able to adjust or take out that slack. But even without that, the timing tool still lays in there flat. So that's still pretty much at a good straight up position. That the distance from the higher portion to the lower portion is 7 thousandths. Now we'll use that, both of these as known goods, and I'll compare the other side. Okay, so now for the bank 1 side, I'm still at the same position where it's zeroed at the same point. And this side's a little bit harder because of the side where the dial indicator is set. So I can try to show you quickly the points again where I measured. So call that there, and I believe it's 926. And then the other side of the exhaust is at 978. And then on the intake side, this one was hard to get a good measurement on the one end. So looks like we are at on the 922. And on this inside edge, I had to use a different measuring method, but I have a number. Okay, so this is basically a drawn out version of the measurements I just took to try to help explain. We'll go with bank 2. And here's your intake cam and exhaust and the points where I measured. And so the point here, obviously, like I showed you, was from 945, and then it tilted upwards to the 952, which was a 7,000th increase. And this was flat out at 947. Now off to bank 1 on the intake. The point furthest away was at 922, and then it tilted upwards to the 974. That was a difference of 52,000, and then the furthest point away on the exhaust was at 926, and then it tilted upwards to 978, and that too was also a difference of 52,000. So the bank 1 cams are both pretty much tilted about the same distance, and it points in the way of where they're tilted this way, both intake and exhaust. And since the engine on this end is rotating clockwise when tilted this way, makes those cams, both cams, be advanced. So with that, there is a good physical comparison from side to side, and lets us know exactly why the codes were being set, and compares it to the scope captures that we have found, where in the bigger picture of it was showing that the exhaust valve was closing sooner compared to the good bank, and so on and so forth. So we're definitely seeing physical evidence here as well, where the cams are in the advanced position, and both of them pretty much the same. That's going to be due to most likely the drive mechanism and stuff, but being what this job is, it is getting complete timing work. Phasers, chain drive tensioners, chain and guides and all that down here as well. So I just wanted to get you an actual physical view of what the timing position of what the timing looks like in its set position for checking and or setting. We're definitely seeing bank 1 be off. Okay, so just a quick shot of all the components that got replaced, and everything in time and torqued. Tensioners have been released, and I spun it around already and locked it back in. And obviously this tool was already fitting before, and now you can see this one sits in there nice as well now. So both sides are now timed, and now just fun task of putting everything back together and installed back in the car. Alright guys, so here is the final product. It is up and running. It's been here for a long time. It was a big job. I have gotten now about 100 miles. Actually, I'll show you quickly. You see on the trip counter, right at 100 miles of driving. No lights, no codes, I'll show you again. So no codes returning, no leaks, no rattles. Everything is good. And it is up and running. Like I said, that whole time, no more lights, no codes. Everything is good and normal. The vehicle is now fixed and ready to go. It's been here a long time. It's going home to its rightful owner, which I thank him as well for letting me work on this and take on this big job. This vehicle is important to him, and trusted me to dive into it this deep. So along with that, we know that the vehicle is fixed. We did see the problem. It is now back to its good normal health. It was definitely cool to see the scope captures and the difference bank to bank, and then see it in person physically once you open up the engine and seeing that the timing was advanced on that one bank. So now that everything's good and set, like I said, nothing else more to do on this other than give it back to the customer, let him enjoy it. And after this, now we can move on to the next one. So hope you liked it and enjoyed it.